consisting of, can you come over here, guys? You didn't see anything there. We have a receiving antenna followed with a detector. So the two components here basically represent the receiver or make up the receiver, and the two components or the two blocks over here make up the transmitter. And then after the detector, we are using here an amplifier and a motor to amplify the signal from the detector and run the motor by the detected or by the received signal. In brief, this system transmits high frequency microwave signal over certain short distance over here for demonstration purposes through a microwave source which generates the microwave signal, and an antenna which radiates the microwave signal as electromagnetic waves, okay, in space. And the waves or the signal being transmitted is detected actually by the receiver through the receiving antenna, and then converted into a simple form of signals, that is DC voltage. So the received microwave signal is converted into an equivalent or a proportional DC voltage, which is then amplified by the amplifier used here, and then the amplified voltage or the amplified DC level is used to run the motor. The motor here, I'm using the motor just for noticing the amount of received signal or indicating the functionality of the link, that we have a radio link and this radio link is functioning by rotating the motor or turning on the motor, which indicates the reception of some energy or some microwave signal at the receiver side. We have here two power supplies, one used to power up the microwave source, just like any electronic circuit or electric system that needs basically an external power supply to work or operate. This microwave source or microwave generator, which generates the high frequency microwave signal, is powered up by about 8 to 9 volt DC supply. We just need to set the supply to 8.5 or 8 to 9 volts to make this function generator or this microwave generator on. And we have another power supply for the amplifier. So the amplifier also needs a power supply to turn it on or to power it up. And by this way here we have, let's say, a complete radio link, a transmitter, a receiver. The transmitter radiates the high frequency signal, the receiver receives the high frequency signal and converts it into a DC voltage. There is a DC voltage from the detector, from this block over here, is usually proportional to the received signal amplitude, the received signal level. The larger the received signal by the receiving antenna, the higher the DC voltage from the detector. But in all means, the received signal is very small compared to what has been transmitted. So therefore, the output from the detector is going to be very small, maybe a few tens of millivolts. So that's why you need an amplifier to boost this voltage level up to a level sufficient to run the motor. Fine? But this is normally the case. Usually radio receivers should be able to detect small signals and process the small signals by having some amplifiers or amplification processors in the receiver. Okay? So there's all receivers, all radio receivers should involve some kind of amplification in order to make use of the small signals being received. You usually receive the small portion of the transmitted power because we have high amount of loss in the radio channel or in the propagation from the transmitter to the receiver. Most of the signal is lost in the space. Okay, I will, sorry, any questions?
Sir?
Yeah.
Aren't microwave waves, aren't microwave dangerous?
Yeah, if you get so close to and if you expose yourself to microwaves for a long period of time. But here we are using, low power. This is basically for experimental purposes. So that's why the distance is short over here. If you want to transmit over large distance, then you have to increase the amount of power being generated. Okay? This is the principle here is similar too. This microwave generator or microwave source This is similar to the one, basically the one used in microwave ovens for generating microwaves, and those microwaves, of course, are used for cooking or warming up food. Okay? Here, electric energy or microwave energy is converted into heat. Okay, and food molecules and all. Okay, if we turn on this power supply and this power supply, sorry, I'll just turn on this power supply which turns on the amplifier, and then this power supply which turns on the microwave generator. The radio link is on now. This generator again generates the high frequency microwave signal, which is a 10 gigahertz signal. 10 gigahertz signal is apparently in the microwave band. Microwave band is the range of frequencies from 300 megahertz to 300 gigahertz. So any system or signal fall in this band is said to be a microwave system or signal. So most wireless communication activities take place actually in this band, from 300 megahertz to 300 gigahertz. This is actually a wide band where many systems or wireless activities can take place or can find a certain frequency, a certain operating frequency. Let's see, we would like to interact with this link now. I claim, or I assume that there is a microwave signal, or electromagnetic wave, traveling from this transmitter to this receiver over almost a straight line. It's not that, that focused, but this antenna is directed and the other antenna is identical, so which means they have to be at line of sight to communicate. Now, the signal traveling out of the, or emitted out of the antenna, relatively, follows a straight line or travels in a straight line while communicating with the receiver, trying to receive or to reach the receiver. What we would like to see actually what happens if we block this link by a metal plate, for instance. This is a metal, like any metallic surface that can exist basically in front of the wave or the transmitter. If we insert the link over here, the link is broken. So this indicates that we have a wireless signal or a wireless wave or electromagnetic wave traveling between the transmitter and the receiver. Why is this? Why the link is broken if we insert a metal plate or a metallic or a conducting surface? This is mainly due to reflection. So conductors are good reflectors for microwaves or radio frequency signals. So an RF signal would be reflected from a good conductor. A good conductors basically cover a wide range of metals and materials, iron, aluminum, copper, and so all these metals actually are good reflectors. They have high conductivity, and therefore they reflect microwaves, so they have high reflection coefficient or high reflection property. Now we can demonstrate the reflection of signal by, you see, moving this antenna away from the receiver. Now we have no line of sight. The two antennas, as I said, are directed, which means they should actually see each other. They should be at line of sight for communication. Now, line of sight is no longer, does not exist, and therefore we can demonstrate reflection by placing the metal plate next to the transmitting antenna. So here the signal is being reflected back towards, the incident signal is reflected back to the receiver. So this demonstrates basic reflection, and metals are good reflectors. Now let's try if we can reflect with, there is some, we have some, but reflection here is much less compared to metal. I can demonstrate this by returning this to line of sight and just insert paper. The paper is not fluffy, so the signal can travel through, can penetrate through with certain amount of reflection. But the reflection is not as significant as let's say, high as reflection by metals or synthetic surfaces. Now we can try even with other types of materials. So this is a plastic. Plastic actually is not is an insulator or dielectric material, and therefore the signal can penetrate through or can travel through plastic. Wood, for instance. By the way, if we are able to measure the received signal on a voltmeter, but it's going to be difficult, we can show it on or a projector or a slide. We can basically see the amount of attenuation for different materials when inserting this piece of material between the transmitter and receiver. So for each new material, we can record a new voltage level, and by this way we can compare the attenuation introduced by inserting an obstacle in the propagation path over here, or in the radio link between the transmitter and receiver for different types of materials. So for wood, for plastic, and then you can compare the attenuation or the penetration of waves through these materials by comparing the output signal or the output voltage level measured with a voltmeter or an oscilloscope or any measuring device. This is, again, if we, guys, as the signal travels in the space between the transmitter and receiver, it interacts with different basically objects and materials, as we just noticed. This is so important actually if you have obstacles. So it's important to determine the amount of power to be transmitted in order to have a functioning link. And also, this is important to ensure that the receiver is going to have sustainable and full functionality with let's say, the obstacles in the environment. So this is actually done by increasing the power. If you increase the power, then you can reach or you can penetrate through even good conducting materials or good conductors. This is dependent on many factors, but you have to increase the amount of power if you have attenuation by obstacles in the radio link. For instance, if you want to communicate with a receiver behind the wall, of course, we have to use the right frequency. We can't use very high frequency because the very high frequency will be subjected to high attenuation while traveling through the wall. And at the same time, we have to increase the power in order to overcome the attenuation introduced by or introduced or caused by this concrete structure. So this is very important in designing wireless systems or wireless networks. They take into consideration the obstacles, the nature of the radio link between the transmitter and receiver. Of course, this is for person communications on the ground. We have other types of communications where you have a line of sight where no obstacles may exist, like satellite communication. You transmit and receive over long distance in a clear path, no obstacles in between. And you need to be at line of sight. But for example, mobile communication, you have to receive while indoor, in a room or a building. The low frequency and the transmission of signals over over a certain geographical area allows multiple users to communicate with a base station with one transmitter without the problems. Unless you are metallic shield, for instance, like a lift, or if you are in the basement or deeply in. So you lose coverage sometimes in certain areas. Yeah? Sometimes even in tunnels and deep basements, car parking slots, you lose coverage. This is due to having some let's say structures around you which attenuate and reflect microwaves away from the receiver. One last